Welcome back to the Marine Hydrodynamics course. So in our last class we ended with the similitude equations, which are similarity ratios of practical importance, and today we'll be looking into another concept which is of ideal fluid flow. So till now we have been deriving equations considering viscosity and other compressible scenarios, but today we'll be talking about ideal fluid flow, which is of practical importance because in many use cases we assume the flow to be ideal, and this really simplifies our problem in fluid hydrodynamics. So what do we mean by ideal fluid flow? So ideal fluid flow consists of two parts. So the first thing which a fluid should satisfy in order to qualify as an ideal fluid is that it should be an inviscid fluid. Inviscid fluid means that the viscosity of the fluid can be assumed or approximated to be 0. So this is the first condition which should be satisfied, and the other the last condition is incompressible fluid. Incompressible fluid. So it should not the density of the fluid cannot be changed. So if a fluid is inviscid and if a fluid is incompressible, then we call it as an ideal fluid, and therefore the flow of the fluid will be known as ideal fluid flow. So now I have assumed, or we have assumed, the viscosity to be nearly 0. Now what are the consequences of that? So from our last class we know that Reynolds number is given as UL by V, where this is viscosity mu, right? And for practical use case scenarios, this quantity, which is the velocity into length, is very high than the viscosity, and therefore this is actually somewhere to the power of it's greater than equal to 10 to the power 6, which is of course much greater than equal to 1, right? And since it is so huge, practically we can assume the viscosity to be 0, right? So what we do is we just neglect the viscous forces, because this was inertial forces divided by viscous forces, and since this is a very large quantity, we can assume the viscosity to be very small and practically to be 0. So this is the concept of ideal fluid flow, that is inviscid plus incompressible flow. Now let's look at the equations which we get with this assumption. So the first equation which we had two elementary equations to solve our problem, that is the continuity equation and the Navier-Stokes equation. So in this case as well, to solve the problem we'll have continuity equation, and since it is an incompressible fluid, the continuity equation will simply be the divergence of velocity equals to 0. So this is the continuity equation, as simple as that. And for the Navier-Stokes equation, what we do is we input the viscosity component as 0, and therefore actually the Navier-Stokes will now get converted to Euler equation, and thus we'll get dv by del v by del t plus velocity gradient of velocity equals to minus 1 by p gradient of pressure minus gj. Alright, so this is nothing but this is the Navier-Stokes equation. So this is the material derivative. We had this as dv by dt, the material derivative of velocity, right? And as you can see here, there is no viscosity term because we have assumed the viscosity to be 0. So these are the two equations which we have for an ideal fluid flow. So from this, of course, now this is a partial differential equation which we have got, both of these equations. And if you must have solved a differential equation, in order to get a particular solution you need to have certain initial conditions, right? And those are actually known as initial value problems. So in a similar way, we require certain initial conditions in order to solve this problem. So what are the initial conditions? And this also we have discussed in our previous classes, that is we'll require some boundary conditions. So boundary conditions here are can be known as initial conditions. So the boundary conditions which we'll have, we have seen that the boundary conditions are of two types, which is the kinematic boundary condition and the dynamic boundary condition. So the kinematic boundary condition which we will have in this case is that there should be no flux. So if you remember, we had seen that there should be no flux and there should be no slip, right, in our Navier-Stokes equations boundary condition. So in this case as well, we should have no flux. No flux would mean that u dot n cap equals to un and v dot n cap. So this is the velocity of the boundary, this is the velocity of the fluid, normal, this is normal to the boundary, this is n cap, right, and that should be equal to un, or a constant. So there should be no flux change. So that is one kinematic boundary condition. And the other kinematic boundary condition was the no slip condition. But since here we have said that the viscosity equals to 0, therefore we do not assume that condition, and therefore we can have a slip condition. So the only kinematic boundary condition which we have here is that there should be no flux at the boundary. This is the only kinematic boundary condition given. And talking about the dynamic boundary condition, so dynamic boundary condition, we should be given the pressure. So pressure should be given at the boundary. So the boundary pressure should be given in order to solve the equation. Now this is the ideal fluid flow. Now we have the continuity, we have Navier-Stokes equation for ideal fluid, we have the kinematic boundary conditions, we have the dynamic boundary conditions, and thus this is just a simple partial differential equation which you need to solve. So that's it about the ideal fluid flow, and this is a pretty short lecture. In our next class we'll dive into the concept of vorticity. What is a vorticity? You are similar with, you can look at your sink basin or something. So you have of course seen water. Suppose this is your basin. Let me try and draw it. So suppose this is something like your basin, and you have water from the tap and the hole, and there's a hole at the bottom, and you must have seen the water circulates in spirals and then goes down the hole or to the drain, right? So that now we need to solve that equation as well. So therefore we learn what vorticity is, and thus we use the concept of vorticity in order to define why that flow is happening, and in order to explain about that flow. So that we look in the next class. It's a pretty interesting thing, and from that we'll also then derive the Bernoulli's equations and other useful stuff. We'll also see an interesting video. So till then, stay safe and thank you.